All right. Hey guys, welcome to Cassandra Lunch 20. Yeah, just share my screen here like this. We've been doing this now almost half a year. So I think by next time we're going to just remove COVID edition because this is something we're going to continue doing for a good while. Cassandra Lunch DC is a byproduct of Cassandra Meetup group in DC and Chicago. We talk about various different topics. Today we're going to be talking about Cassandra read and write path, which is how Cassandra manages to store data and retrieve data at high speeds. This is a fascinating subject for me because I mean I have studied databases, but I can definitively tell you how Cassandra works because I think it's fairly simple how it works. And it's open source, so you can go read exactly the code that does all this stuff too. Akwi and I are co-organizers. Love to get help. As a co-organizer, you get to get speakers, get different sponsors. Right now we don't really need sponsors, but once you are a co-organizer, you can start doing things like Data Community DC. So there's a panel for Data Week DC coming up that I've been invited on, and if you want to do stuff like that, get onto panels. Volunteering in the community is a great way. Data Community DC is a large group of diverse people in the DC area. We're actually a group of several meetups. But in this group, we cover data stacks, Cassandra, anything like Cassandra, so Scala, Cosmos, managed key spaces for Cassandra. I think that's what it's called now. Normally, we'd use this time to have people introduce themselves. I don't see anybody new. It's fine. Group roles, if you have a question, go ahead and ask it. Be polite. We can ask it in the chat. Let's see. DataStax is a partner and a sponsor. So is GW. So are Eastern Foundry and Wavicle. Our organizational sponsors, we have General Assembly, Capital One, American University. These are sponsors that help fund the whole nonprofit. So Data Community DC is a nonprofit. Any announcements? We do have a couple of events coming up. Well, I'm going to show this screenshot, but we do record Cassandra Lunch and put it on YouTube. So if you Google Cassandra Lunch, you'll find YouTube videos about all the talks. There's also Cassandra.Link, where any of the resources we cover in these sessions, or if somebody's doing a presentation, a slide, a video, all of it eventually makes its way into Cassandra.Link. All right. So let me go ahead and, oh yeah, events. There's weekly workshops with DataStax. There's this weekly lunch. We're actually on deck for October 6th for a talk on how to make a real-time API with Kafka and Cassandra. This is work building on the first workshop we gave, which was how to make a Cassandra API with Node.js and Python. The work has been done by team members at our company, Anant, on both fronts. This week, today, there's a talk on Introduction to DataStax Graph. Tomorrow, there's a talk on comparison of the different Cassandra as a service variants, so Astra, Cosmos, and AWS key spaces. I'm actually looking forward to that one. And if you want to find out about other events, feel free to go to our website, subscribe to the mailing list, or subscribe to the YouTube channel, this one that you may be watching if you're not watching it live.
Yeah.
All right. Cool. All right. So Cassandra read and write paths can be explained in roughly 4 general, categories: write path, read path, obviously, but then there's the update delete path, and then there's the maintenance path, which is what's happening in the background. There are a bunch of resources that I'm going to refer to. These are all on Cassandra.Link, so you can look for it. The best ones are the ones I've shown here. Well, not all of them, I would say. This one is the top, which is the DataStax article on how Cassandra reads and writes data. And then Jeff Carpenter's explanation of Cassandra architecture is good. And then I believe these are simplistic, but they get the point across. So let's talk about just briefly getting into the right path and all this. We're not going to cover how Cassandra replicates data per se today. Okay, that's a different topic of how it replicates and spreads data. Today we're going to talk about how on a given node, how Cassandra manages data. Then the cluster does the management across replicas, but ultimately it comes down to the node level. There are a couple of visuals that are commonly, I would say, recognized in the industry. One is this one. Okay. And if you're an expert, you should be able to redraw this diagram and explain what happens. You don't necessarily have to know everything that's getting created in an SS table, although that's like master level. But just as a basic, subject matter expert, a specialist, you should definitely know what's happening here, and we'll talk about that. And then at the right path, so that's the right path. In the read path, there's a slightly different diagram, which is a little bit more complex, but you should still be able to explain what's happening here. Okay. All right. So obviously, before we can read something, we got to figure out how it's written. I have my outline of it, and then I'll go back to that outline because that's always going to be there. So right path, generally, the first thing that happens is your application talks to a coordinator. This is any coordinator, by the way. Any coordinator means any node in the cluster. That coordinator leverages a partitioner to figure out whether or not your data, when you're inserting with a primary key, you have to give it a primary key, whether it belongs on that node or it needs to go to a different node. And then in parallel, between replicas 1 through n, instructions get sent. How that happens, we're not going to talk about that today. But all of the replicas, and it's generally depending on like your consistency level, right? Again, we're going to talk about that. But instructions get sent. If it's a high consistency level, it's synchronous or higher synchronicity, versus if it's a lower consistency level, then it's lower synchronicity. But it sends instructions, and then the node that actually needs to have that data stored, the right server that token is assigned to, it logs the data in a commit log. So important note, this is going to disk. Simultaneously, it's getting written to memtable, which is a in-memory representation of that data. And then it acknowledges and it says, I got it. And again, depending on your consistency level, this is happening more parallel, less parallel, in sync or not. And then every now and then, when the mem table gets filled, that data gets flushes from the mem table into SS tables. Something else happens. All data in the commit log until that point is cleaned. Okay? And this is the durability. This is what makes Cassandra durable, right? It's in memory. It's in the commit log. If the server crashes, it replays the commit log and it gets back everything into memory. If memory is full, it goes from the mem table to the SS tables. Commit log gets cleaned. At that point, if the server crashes, it's all in the SS tables. Any questions about the write path? So when I say parallel async, this is happening in the background, right? This is not happening when you write the data. It's just kind of happening in the background. Take a look at that picture again. Data comes into, at this point, beyond the coordinator on that particular machine, simultaneously goes to commit log and to the mem table. Every now and then it's flushed, put into the SS table, the commit log is cleaned. Now, when it's flushed, a bunch of stuff is being stored on disk. So here's the data, right? Data.db. There's the primary index with the row keys with pointers to their positions in the data file. The Bloom filter, this is actually stored in memory, but it's persisted to disk. Compression information, file holding information about uncompressed data length, chunk offsets, other compression. It's just meta information. Statistics, so when you run table stats, right? And then there's also specific stats about the SS table. All this stuff is in the statistics DB. The digest, this is useful because when we're doing kind of comparisons of SS tables, you don't want to necessarily compare all the data. You just want to check the checksum. TRC32 for the chunks in the uncompressed file. Again, related to digest. SS table index summary, which is for everything that is in the SS tables. This is a just a partition index at the high level, not every single row, just the high level partition index. And then this is the table of contents for all of the components of the SS table. All. And then sometimes we have secondary indexes that's stored in different DB files. But at a high level, just think about all of this as SS table, right? It persists to disk. So where are the three areas where Cassandra stores information? Mem table in memory, commit log on disk, and SS table. And an SS table is a collection of all of this stuff. Any questions? Okay. Now we have data in Cassandra on the disk. Sometimes we have to update and delete information. Data updates are the same as inserts. And when I say they're the same, in fact, it's called an upsert. It goes and it updates the mem table. It puts it in the commit log. When the thing flushes, the new mem table object that as it exists in time gets flushed, and it makes new SS tables. And then these SS tables get compacted. So we'll talk about compaction in a second. But there's no time for Cassandra to go look up where the old data is and then verify it and then update it. It just keeps adding data, keeps upserting, keeps appending. And every now and then the compaction makes it more optimal. So if you did 5 different writes or updates to a row, the way it knows to give you the latest information generally is the mem table already has the latest information because it's in memory. But if it's not in memory and it has to get it from the disk, it actually reconciles it. By the time you get it in the mem table, it's reconciled. And there's a performance, we'll talk about, how do write patterns affect the reads? We'll talk about that in a second. Deleted, how is data deleted? Similarly, instead of going and finding the information and then deleting it from disk, generally what we do is we put a marker to say, delete this. And we talked about this in a previous talk about what tombstones are, what they look like in the SS table. But that's how data is deleted in Cassandra. It is not a special thing. It's just insert, update, delete. They're all appends to the same information. And as data is updated, simultaneously, we end up having to update indices. Right? So the more indexes you have, the more index files need to be managed. Secondary index, storage, attached index. We'll talk more about that in another session. So next important part about how data is managed in Cassandra. So we just talked about writing data, and we just talked about it just keeps appending information, right? How is it any different from, just saving files in S3 or using HBase? Well, it's slightly different because in the compaction process, we have different compaction strategies, and the different compaction strategies allow us to optimize for reads or for writes or for both. And that process of maintenance is called compaction. As you can imagine, a bunch of SS tables get written with appends and stale data, okay? At the end of the compaction, that data is merged. All the old data is evicted. Data is deleted. And then it gets compacted into a smaller SS table. That is what compaction is. Taking a bunch of different writes, merging it together. So it's kind of like a commit log, right? You have a commit log taking every single thing that came in. It gets put into SS table. So for that time, it's a commit of what the data is at that time as it existed in the mem table. And then all of these little quote commits get merged into one commit. Different compaction strategies. So size-tiered compaction basically says have, let's say, 4 of a certain size, no more than that. So what happens is there'll be 3, there'll be 3, there'll be 3, and there'll be 3. When this thing gets compacted into something like this, and there'll be 4 of these, that's the threshold. So then all of this will get compacted, and there'll be another 4th one at this size. Then that will get compacted, and there'll be another big one at this size, and then this will all get compacted, and there'll be 1 at the highest size tier. And it just continues. This happens to be the best for write-intensive workloads. It's actually pretty good for read-intensive as well. You just have to kind of tune the thresholds. Level compaction keeps certain things at certain levels. And it's basically the size level. So there'll be like a level 1 of, let's say, 160 megabytes, and the next one will be like twice that, right? And it's generally optimized for read. Why is it optimal for read? Because there's less updates coming in. And it just ends up having a bigger and bigger SS table, where you know everything is, right? So you don't have to scan many files to get to the data. There aren't going to be 16 SS tables. There's just a few of them to look at. Then there's something called time window compaction strategy, which is great for, again, writing data, but in a time series. And what happens is data gets put into these windows, and at the end of that window, everything is compacted into one SS table. And if we evict that data with time to live, meaning this data is now old, then the oldest data will get kicked off, and this whole SS table will just get deleted. It won't have to go through several different files to say this data is old, it needs to be deleted. So time window compaction strategy makes sense if your data is coming in a time series. Now, in the middle of, having compacted one time window and the new one, it uses size tiered compaction up until that point, okay, within the time window. Data tiered compaction was the old time window compaction. It's been deprecated. Don't use it. It doesn't work. Time window compaction was a newer version of that. Which one is the best strategy? There's not a very simple heuristic to do this. But people generally have, advice. It depends. You just have to kind of see what your service level agreement is, how much data is coming in, how much data is getting read, what type of data it is, how big the data is. And then, even if you use LCS because it's read heavy, you may realize that, hey, one big SS table that is 1 terabyte is not good. We need to split it. So we need to split up this SS table. So size-tiered compaction, you're pretty good. Until you really are read heavy, size-tiered compaction pretty much does everything you need. Okay. Another thing that happens in the background, and this is cross-node, is repairs, in which it compares SS tables with other SS tables. Each replica of the data, right? Each replica of the data will be consistent across the different replicas. So in order for the system to have consistency, the repairs are done at the SS table level. It has to walk through all the tokens. It's not part of the read and write. It's just, it ensures that for the most part, it's keeping things consistent for you. And you have to either use Node Tool Repair or Cassandra Reaper or whatever to do this, but that's a way to maintain that data. And finally, we're at read path. Yeah, go ahead. Is there a question?
Oh yeah, sorry. I just had a question about the write path again. How does Cassandra decide what's the most up-to-date information? Is it just get timestamped when it hits the coordinator node, or how does it decide, oh, it got updated with this update before that update? If there's multiple updates for the same record.
Yeah, absolutely. It all comes down to when it hit kind of like the commit log, because that's the first level of durability. Because up until then, like the mem table, like let's say that machine crashes, If it's not in the commit log, it's not real. So what does happen is before it gets to the commit log, sometimes if the node is down, it gets put into what's called a hint, and it's not quite reconciled yet. So the coordinator gives it the metadata, and you can actually tune, like using things like batches. You can say, this is the time that I want it to be inserted. You can set those things. But what you said is accurate, but ultimately it's what's stored in the commit log. That's what matters. And when you do a kind of, yeah, go ahead.
Oh, I was just, so it's the commit log on the coordinator node, or like how do they, I mean, if two different nodes are going to get the data at different times, I mean, slightly different, but
well,
which commit log does it say, like, this is the authoritative?
Yeah, so the coordinator gives the timestamp, because you can configure that using things like batch logs and things like that, right? You can say, I want all these inserts to go in at this timestamp, right? The coordinator accepts that information. It relays it, but it doesn't mean anything until it hits the commit log. Once it's in the commit log, then it's real. Do you understand what I'm saying? Even if
Got
it's
it. Yeah, so it's only
yeah, it's only acknowledged once it's in the commit log. Up until that point, it's ephemeral information.
Got it. Got it. Thanks.
Yeah, that's super important to realize. Like it's in the wind until it hits the commit log, essentially. But because it hits the commit log and the mem table simultaneously, it becomes accessible, and that timestamp is how it's sorted. In mem table, it gets updated immediately because it's in memory. But every now and then when you have a flush, and you have, let's say, 5 SS tables with a partition that's across 5 SS tables, when it reconciles it based on what it got flushed as.
And then, sorry, another question is, what's the advantage of having a mem table if you're going to have to read the SS table anyway?
You don't read it. Well, we'll talk about the read path in a second. You don't have to read that.
Oh, yeah, right. Totally. Sorry. Got it. Okay.
Yeah, it's not all the time. That's another thing what makes it different from like HBase. Is the mem table makes it available immediately. So then going on to the read path, generally you have the coordinator. The coordinator directs you to the right machine, and in the first replica that it goes to, it does all of this. It doesn't necessarily need to do it for all of the other ones. It just gets a digest. And if the digest matches the one that it's getting it from, then we're good. Otherwise, it forces a refresh of the ones that are off. Or it figures out what is the latest version of the data, and then it gets that one. Again, I'm not going to cover how it's managing, between the different replicas, but just acknowledge that when we do a read, we don't necessarily have to go through all of this on every single machine. It's just whatever machine it decides it needs to get it from, it gets it from there. So there's a visual, but just let's walk through the general steps first. The first thing it says is it goes to the mem table, right? In the mem table, it checks to see if there's a row cache, if it's enabled, and if it's there, it gets that. If it's not there, it goes into the Bloom filter. If it's not there, it goes to the key cache. At this point, we're kind of in memory up here. Then it goes to the compression offset. If it's in the cache, if it's not, it checks the partition memory. At this point, we're now talking at the disk level. Partition memory is checked, partition index is accessed. Then it goes to the location from the offset, gets the data from SS table and gets it. Sounds complicated. It is more complicated than the read path, but that's because we're talking about two areas of data, memory and disk. So right, this is a hole in the memory. Read request comes in, Bloom filter tells it, actually even before the Bloom filter, there's a row cache, right? It sees if it's that particular row exists. If it exists as a full row, it gets it. Otherwise, it says, go to the, get me the partition if it's available, which then says, here's my summary of that information, and goes to the partition index, goes to the compression offset back in memory, gets it from SS table. At this point, if it has a version of the row or the partition in memory, it just returns that. It doesn't have to go to the disk. And this is how the row cache and the key cache kind of works. The application requests a hot, frequently accessed row, and that's the row cache. Application requests data not in row cache, but whose key is cached, that's the key cache. So this is the full data. This is just the pointer to the key cache. Then it picks it up from SS table, brings it into mem table, and sends it back. And at this point, this data is back into the row cache. So, long story short, if you want to have a very, very, very fast Cassandra, have a ton of memory, like a ton of memory, and have a big row cache and a big key cache. It'll just keep everything current in memory. And if it's not, it goes to the disk, essentially finds it and brings it back. So, any questions here?
So
Here's
the mem table, oh, sorry.
Yeah, go ahead.
The mem table, it's not like, it doesn't have a, it's not like the commit log where it's writing, oh, here's all the writes and reads. It's actually got the information organized by the primary key, and you can, there's only one record in the mem table for one database record.
Yeah. In fact, in the mem table, you have the whole partition.
Oh,
you generally
wow.
have the whole partition.
Okay.
Yeah. That's why you don't want to have big partitions.
But if you flush it, does it still have the whole partition still?
Not unless you read it again.
I see. Got it.
Compression offset is in memory, or is it reads from the disk?
Compression offset is in memory. It just keeps it updated. It's much faster to get that information from memory than it is. It is persistent to disk, but it's the type of information you want to get immediately. It's not mem table. It's just in memory.
Yeah, because see, once compression is done for the past data, how it will know? Okay, in the sense, if it is in memory, all the past compression, it has to have that kind of history, right? It will be.
So I think you're conflating two things. Having the compression offset is just where in the file that data exists. You see what I'm saying?
Yeah. Okay.
Just the offset. So like I put Rahul's information, I compressed it between this location in the file and this location in the file. That's what Rahul's information is.
Okay.
That's all that's stored.
Okay.
It's basically a series of indexes, right?
Yeah.
It's just a series of indexes to get you to where you need to be. The last one is where on disk is it? Because it's compressed, we need to know exactly what the offset is from where it begins, where the file begins, basically. That's what the offset means.
Okay. That means if we are doing frequently doing a compression,
it's not compaction offset.
Oh, sorry.
It's the compression offset.
Yeah.
Compression in the sense that just data compression. See, SS tables, if you expand it, it's a JSON thing. It looks like JSON. okay?
Yeah.
But we're not going to store it as text. That's like Hadoop world, H-based world. We compress it into like a binary database. It's still SS table. It's still a sorted string table. It's just compressed. But in the compressed file, we need to know the pointer in the file where to pick up that particular thing. So a partition will be in between pointer 5 and 15, for example. We get the data, we uncompress it. You get where I'm coming from?
No, my only, I got the point. The only my thing is, see, if my data is huge, okay, I'm doing the compression, okay, but if my data is huge, then this compression offset means it's sitting completely in memory. That's what my question was.
It sits in disk, but it's accessible in memory, because when it's in memory, it's much faster for the system to go and say, where is this partition data? So this is the partition index, right? Partition index tells you, okay, in the compression offset, for this partition, here's the start and end of the file. Then once you get it from the SS table. Even if this is stored in disk, it won't be as fast unless it's stored in memory.
Yeah, okay.
Okay, what if you have a terabyte SS table? Your compression offsets, even if it's a gigabyte, right? You're not going to read a gigabyte file. If you have it in memory, it'll be way faster to say, for this partition, where are the start and end? Oh, here it is. Boom. Done.
Yeah.
Okay.
Yeah.
Cool. You can go dig deep into this. Here you go, right? 1 to 3 GB per terabyte compressed. You have to have more memory as you have more data. All this stuff is tunable. The Bloom filter is tunable. The key cache is tunable. Everything is tunable. But for the most part, you don't hit these issues of tuning until you hit a performance issue. And more than likely, you don't need to mess with any of this stuff before you have to test the data model. You know, we'll talk about the data model, but the data model is the primary area of tuning in Cassandra. Then we get into these things like, you know, compaction strategy, topology, memory settings. But, you know, you have to fundamentally understand how the data is read and written and maintained to understand the sequence of events. So that when you understand the sequence of events and you're looking at Elastic and Kibana or Op Center, you start to see these patterns. Oh, when the data comes in with this much frequency, memory usage goes up. And then there's mem tables, flushes come pending, and then there's a bunch of flushes that happen. Disk IO goes up because we read from the commit log and we saved to the SS table. Okay, cool. When we continuously get more and more data coming in, then SS tables need to be compacted. There's compactions pending, and the compactions happen, and the disk IO goes down. But while the compaction is happening, CPU usage and memory usage is high. While the data is coming in, while the compaction is happening, while the flushes are happening, at the same time, there's lots of reads coming in. So really what you're learning right now, right, the read and write path is at the bottom level, but it's all a dance. There's like 16 dancers that are always dancing in Cassandra. And that's the topic of next week is the different stages. I'll give you a preview. I thought I could cover this today, but it's just too much. Here are the different threads or dancers in Cassandra. They're all running all the time with different settings. Compaction executor is running compactions based on thresholds. Anti-entropy runs repairs based on settings or prompts from node tool repair. Commit log archiver, right? When the thing flushes, this thing is kicked off. What is responsible for read and write stage? Okay, well, let's see. Memtable flush writer, memtable post flush, memtable reclaim memory. So this is just for memtable stuff. Mutation deals with inserts, updates, schema merges, commit log replays, or hints in progress. This has anything to do with writes. Native transport requests, so any CQL. This is what the coordinator does. It responds to CQL and then breaks it apart into internal things. Read stage does all the things in the read. Read repair is different. We didn't talk about read repair. Actually, I'm gonna come back to it, but read repair is a part of the read path. And given some percentage, it runs a repair process on some of the process when you read. We'll talk about this when we talk next week. Request response. This is internode. So of these, so one, oops, how many do we have total? 20 different stages. 1, 2, kind of, but really 3, 4, 5, 6, no, not that one. Sending missed mutations, okay, I guess, no, not really. So 1, 2, 3, 4, 5, 6, 7 out of 20 are related to read and write path. So you can go and kind of classify these as, I guess, anti-entropies. Well, there's general maintenance and then there's internode. I don't know about you, but this is a very bite-sized database. If I can explain to you how the whole system works in 20 threads, that's kind of amazing, right? The whole Cassandra system literally runs as threads between these different threads, messages between the different threads. That's why I like Cassandra. Yeah, go ahead.
Sorry. I have one small query. See, is the read path is impacted by any SASE index or secondary index or Solar indexes?
Yes. So in so like right here, okay, when you're doing a query, basically between here, the partition key, and the partition summary, there's a better way to find information, and that's that index. And that's a fast forward directly into the compression offsets. That's one part of it. The other part of it is that if it's using Solar, which is not part of Cassandra, it's part of DataStax, Solar also stores data. And you don't even have to pull up the partition. You can just go get data from Solar. So that's a different story. But yeah, it basically shortcuts this stuff right here.
Okay.
This is as good as memory, right? If you know exactly where the key is, you get it. And by the way, it's remember that if you don't have the primary key, right, then your coordinator has to basically figure out where to go. And so the SASE index is the next place it talks to. So SASE index, et cetera, has its own read path, right? It's SS table storage attached. Secondary storage attached, SS table attached secondary index, right? that data, the data for the index is then being stored in SS table. So then it has its own read path, but it's still going to be faster to look at that to find information than to do a scan. Here, we're assuming you know the partition.
Okay.
Right? You know the partition key to get this information. Otherwise, you have to scan it.
Yeah.
Okay.
Yeah.
So again, a kind of a preview of next week. Basically, when you run node tool pstats, it shows you what's happening, right? All of these things are happening, and it kind of looks like this: what is active, what is pending, what is completed, what is blocked. And then these are the messages that go between the nodes. So essentially, if something is like happening where there's a bunch of blocked threads or dropped messages, it means that you're running out of memory CPU, or you're hitting a bandwidth issue with disk or with network. Okay, this is kind of the underlying health of the system comes down to this. And although this blog post is old, it kind of talks about how different nodes, right, send messages between these different stages to do things for you. And then it goes from node 1 to 2 to 1 to 2, to 1 to 1. Cool. All right. So any questions about read and write path?
You'll save it for next week.
Cool.
Thanks.
All right, guys. You guys have a wonderful rest of the week. We'll meet same time, same place. Remember that you can always subscribe to the playlist for Cassandra Lunch. Go to Cassandra.Link and sign up for the newsletter. Or if you want to just check out the events, go to anant.us/events. Thanks, guys. See you all next week. Bye-bye.